This is the title. This is Queen's University, and if you go around the corner, this is the building where I work. There is a plaque devoted to John Stuart Bell of Bell's theorem, and he studied in that building. He comes from Belfast, which is what quite a few people don't know. Moving on. Positrons. I would like to apologize to everyone who deals with positrons more or less on a daily basis for a couple of introductory slides, but for the benefit of everyone, I'll go through them anyway. Of course, positrons were the first antiparticles to have been discovered. Theoretical prediction was done by Gribakin, and there is a really lovely quote. Following up in time, we can assume that in the world as we know it, all and not nearly all of the negative energy states for electrons are occupied. A whole, if there were one, would be a new kind of particle unknown to experimental physics, having the same mass and opposite charge to an electron. We may call such a particle an anti-electron. We should not expect to find any of them in nature on account of their rapid rate of recombination with electrons. But if they could be produced experimentally in high vacuum, they would be quite stable and amenable to observation. Interestingly, it took Dirac 3 years from the time he wrote down his relativistic electron equation to realizing what the negative, how to properly interpret the negative energy solutions. Of course, they were observed about a year later by Anderson, and Anderson himself, he published 2 papers back to back, a very short account in Science and a big paper in Nature. So some of the quotes are, the specific ionization is close to that for an electron of the same curvature, hence indicating a positively charged particle comparable in mass and magnitude of charge with an electron. And he was looking at the tracks in Wilson's chamber from cosmic rays. These particles will be called positrons. That's where the term comes from the Fizerev paper. The greatest symmetry, this is a wonderful insight, right there and then. The greatest symmetry, however, between the positive and negative charges revealed by the discovery of the positron should provide a stimulus to search for evidence of the existence of negative protons. And these are, of course, antiprotons. So he immediately realized that there should be antiparticles to other constituents of matter. Interestingly, he was not the first to observe these directly curved tracks. Some 4 years ago, 3 years ago, Dmitry Skodoltsin, who graduated from alma mater of mine at St. Petersburg Polytechnical Institute, he was one of the first guys to discover cosmic rays, and he did see the wrong tracks, but just didn't pay attention. He was too excited to be seeing cosmic rays at all. This is him at about the same time, and I couldn't possibly, the webpage I found him on, there was a picture of him and his wife, and I just couldn't separate. And also Chung-Yao Chow, working in Caltech, and looking at gamma rays interacting with matter, had clear, what we may now call clear signatures of positrons, but that wasn't realized at the time. Of course, positrons are fundamental constituents of quantum electrodynamics, of the Standard Model. Of course, they are heavily involved with the question that we have unanswered yet, why is such matter-antimatter asymmetry of the world? And there are other sides to them. There's copious production of positrons in the galaxy. They are at the heart of this medical technique of positron emission tomography. They are widely used as probes of condensed matter. They are not that exotic, after all. So the uses of positrons, a very quick overview. This is how they are seen in astrophysics. This is the signal that comes from the galaxy. This is the center of the galaxy. And the amount of production is quite large. 15 billion tons of positrons annihilated every second. So there must be a source. This is a positron emission tomography machine. This is the kind of image that one gets by detecting 2 gamma quanta produced by positron annihilation. Positrons in this case come from some radioisotopes. And one can image the body, one can image the brain, one can see what happens with the onset of Alzheimer's, etc. And the condensed matter spectroscopy with the use of positrons looks approximately like this. A positron is sent towards a piece of material. It bounces around, slows down, gets trapped, for example, in a defect. And so one can study the defects, vacancies, doping, surfaces, depth profiling, sizes of pores, phase transitions, etc., etc. This is a predatory technique for quite a good number of condensed matter scientists. When positrons interact with matter, this is the energy scale. And I will be going down the energy scale because this is what happens to a fast positron when it interacts with matter. of course, can make ionizing collisions, kicking out electrons. It can excite atoms, which it encounters at yet lower energies. It can still form positronium. Maybe I'll say a word about positronium. Positronium, this is the best illustration to the positronium principle I've got. Apologies to those who've seen the picture. You can clearly see a particle and an antiparticle, positively charged and negatively charged, bound by what is the Coulomb force here represented by the lady in green. Positronium comes into varieties. There is a spin zero positronium that annihilates very quickly in a fraction of a nanosecond, and its triplet cousin, orthopositronium, that lives about 1,000 times longer. And this is a really long time, so positronium, even if it's in the ground state, can be studied, can be regarded as a stable particle on the atomic time scales. Going further down in energy, there's elastic scattering. If the positron hasn't got enough energy to do any other damage, but it can also annihilate with one of the atomic electrons, producing a positive ion and two gamma rays. When it collides with molecules, there's this big variety of phenomena. Molecules have vibrations, and this is really important for positron annihilation in molecules, and I'll be mentioning this later on. And at negative energies, positrons do form bound states with atoms. They can form also bound states with molecules. And the bits of this diagram that I'll be focusing on will be this one here, this one here, and there will also be positronium collisions. So here is the plan. I want to overview positron scattering and annihilation of noble gas atoms, in particular touch these vertex enhancement factors. The statement that is not on any of the slides, but the one that I want to make, is that we now have a pretty much complete understanding of the interaction of low energy positrons with noble gas atoms as far as all the deep intricacies and details are concerned. Then we will talk about positronium scattering from noble gas atoms at intermediate energies, and we'll solve the missing positron puzzle. And then we'll look at positron binding to polar molecules. So I'm covering annihilation, positronium scattering, binding. This is the first part. Dermot Green is responsible for the large part of it, and he even got a medal for his poster that he presented at the IOP weekend in Ireland for this work. Positron-atom interaction. Again, to those who do not think about positrons every day, at small distances, positrons are strongly repelled by atomic nuclei. The static atomic potential for the positron is repulsive. Of course, when the positron approaches the neutral target, it polarizes it and draws the electrons towards itself, and there is an attractive polarization potential here. But positrons can also do something else. They can form positronium virtually, even if the energy of the positron is not enough to elope together with the electron. Something along the lines of covalent binding happens. The electron can either feel the potential of the atom where it sits bound by the ionization potential, or it will hop to the positron and be part of positronium. And this toing and froing of the electron is an extra bit of attraction. Of course, this is all kind of hand-waving in a big picture in the mind, but these pictures can be put to an exact calculation. One can describe this process mathematically either as a picture or as an equation, so one can compute these interactions. And for the other one, well, positronium, we should allow the positron and the electron represented by these lines to interact, not just once, but twice, 3 times, as many times as they like. So this would be the virtual positronium contribution. Now, when it comes to doing the actual calculation, we can compute the positron-atom correlation potential, which covers all of these effects: polarization, virtual positronium formation, some higher order corrections. And if you don't like, if you don't believe in pictures, then I hope you believe in the equations. So these can be computed without too much trouble on the computer. On a normal computer, you don't need a supercomputer, and there are some references at the bottom. So what do we do? When we consider positron-atom scattering, and this is just a single example, the S-wave phase shift for positron scattering from krypton. The basic level of theory, the static repulsion, is down there. Then you can include the polarization effect that gives the dashed line. Then you can include third-order correction, it's this line. Then you can include the polarization and the virtual positronium formation. And when you include everything, you end up over here. So all these are significant and large contributions. Forget about any one of them, and you don't get it right. But if you do get this right for the S wave and the P wave and the D wave, then you can obtain, you can see solid black curves there. I apologize for not having many references here. But the solid black curve is the many-body theory calculation, and the black crosses are the most recent and accurate experimental data. There's only one other reference to the theory calculation from Perth. Dotted line is the most recent and the most accurate of the other calculations. You can just about see them, for example, here. Say in Zealand, the dotted line and the solid black line are quite close. You can see that the early experiments produced quite a bit of scatter, but nowadays theory and experiment pretty much converged for all energies up to positron information threshold. Moving on. Positron annihilation, that's a more interesting question. We express the cross-section for annihilation in terms of the basic electron-positron annihilation and the dimensionless number factor Z effective, computing which involves the whole electron-positron wave function, all the electrons and the positron can meet each of the electrons through these delta functions. It's quite a beast to compute. But since we have the many-body theory, Z effective would be calculated in terms of these diagrams, which makes it quite a bit easier. And you can see how these diagrams, they also correspond to some analytical formulae here, so that's what we compute. And when we do, the red curve is the positron annihilation parameter Z effective for xenon. It is hugely enhanced at low energies. This is logarithmic scale. It is quite close to the only measurement that exists. These are the solid circle, and the experiment comes from UCSD, from Cliff Circus group. We can also look at thermally averaged room temperatures at effective values that have been established quite some time. And we can see that this is our theory, this is experiment. There is some uncertainty due to density effects in xenon, but pretty much we get it all to within a few %. And that means that we know exactly what the electron-positron wave function is at short separations. This is what Dermot got his prize for. This is borrowed from his talk. It's really artistic. This shows the annihilation between the positron and the electron in free space, producing two gammas in the center of mass frame. These will have equal kinetic energies, 511 kiloelectron volt. When the positron annihilates with an atomic electron, the atomic electron brings its own momentum. So the electron-positron pair has a non-zero momentum, and the two photons are Doppler shifted, red shifted and blue shifted, and they are also not quite back-to-back. So the energies of the photons will be mc squared plus epsilon and minus epsilon, and this is the Doppler shift. It's several kiloelectron volts. So instead of observing a delta function by plane at 511 kiloelectron volt, we see a broadened line known as the gamma spectrum. And in the next following few slides, I will be showing it as a function of epsilon, a number from 0 to several keV, essentially. These are the formulae that are involved. There's electron-positron annihilation amplitude. These are the terms that we include. And this is what we compute. This is shown for krypton. And let's just focus on one of the orbitals. Positrons annihilating in the 4p orbital. The basic level of theory, static atomic potential, no correlations included, gives this dashed curve. And the final result is up here. And you can see there are two orders of magnitude enhancements, although the shape of the line is quite close. And we do not jump from here to there. We include the vertex corrections. We replace the positron static wave function by the correct wave function in the correlation potential, and ultimately get the red curve. And you can also do the same for inner orbitals. Correlation played a slightly smaller role, and this enhancement going from the static wave function to the true positron wave function just as well. That's how you build the annihilation spectrum. Positrons can annihilate in the valence orbitals, on the subvalence orbitals, on the inner orbitals, and in the end you get the green curve. Then you put it together with experiment. Positron annihilation on the valence shells gives the dashed line. The core gives the chain curve. When you add the two together, it's the solid curve, and it's quite good agreement with experiment. If you do the static Hartree-Fock, it's a mystery. It underestimates the absolute magnitude by 2 orders of magnitude, but the shape of the spectrum is just about right. And we have similarly good agreement for argon krypton. That's where the spectra have been measured. There is an interesting quantity that is the outcome of one of the outcomes of the theory. If you divide the best possible annihilation probabilities and effective with all the corrections included over the most basic one, you get the so-called enhancement factor. And when we computed these enhancement factor from the theory and plotted them as a function of the ionization energy of the atom, they all line up in a single curve. So what we have learned using many-body theory, that this quantity, which is so difficult to calculate, can be easily parameterized. It can be parameterized in terms of this formula. The constants come from the fit, and anyone who wants to calculate positron annihilation rates in molecules and solids are very welcome to use these enhancement factors and multiply the independent particle approximation result by these to get quite accurate annihilation rates. There we go. Now, positronium scattering from noble gas atoms at intermediate energies, solving the missing positron puzzle. This is work done together with Ilya Fabrikant. It started with his email, and then I replied to that email, and we ended up writing a couple of papers on the subject. So what's the puzzle? The motivation came from the experiment done at UCL. This is a picture from the science paper. They succeeded in measuring positronium total scattering cross-sections, which are the experimental data with error bars, and quite ingeniously realized that if they plot this as a function of the velocity of the projectile, there's a very interesting comparison with electron scattering, positron scattering, and positronium scattering. And in all of these cases, positronium scatters almost exactly like electrons do for the same velocity. So this is what they call the missing positron. The positron is still part of positronium, but it looks like it makes no difference to the scattering of the particle. So what's going on here? In order to, the obvious difference, electrons are point-like charged. They are attracted to the atom asymptotically by this potential. Positronium is opposite neutral. The potential asymptotically is 1 over R 1 over R to the 6. What's the role of the positron? As if it's not there. Okay, so we seek answers along the lines of the impulse approximation, and the physical assumption, which is true, positronium is weakly bound. Its ionization potential is 6.8 electron volts. It is diffuse compared to noble gas atoms, where the electrons move faster. So when we compute the scattering process of the positronium going from some initial state to final state, during the scattering process, we can assume that either only the electron or only the positron interact with the target, and then the amplitude becomes the sum of two terms, each containing the electron scattering amplitude or the positron scattering amplitude. So all the parameters can be defined, but the physics that I would like you to keep in mind is that positronium is diffuse, the noble gas atom is small, and only one particle interacts with it at a time. That's the physical assumption. And then you can even show theoretically that the positronium cross-section is equal to the elastic electron scattering cross-section with some assumptions. Then the calculation involves parameterizing the electron and computing electron and positron scattering amplitudes. Here is the result. And you just need to pay attention to the black curve. This is the positronium krypton scattering. And this is how it goes alongside the experiment here. Very similar picture in argon. The positronium cross-section by itself is very low. It's similarly low in argon. This is why it does have a small effect on the scattering in this energy range. But at low energy, something different happens. And that's the whole new story. So the impulse approximation explains the similarity observed by experimentalists in quite a good range of velocities. The underlying physics of the positronium is diffuse, but then it clearly breaks down at low energies. It produces some physical growth, and we have looked at the positronium being scattered as a whole to fix this little problem. Moving on. Our calculation was approximate. Some people claim that they can run their computers, they can do much better job, and I wanted to quote from Valentin Ostrovsky, who was quite a regular attendant at these conferences before he died in 2006, I think. To understand the issue properly, it is essential to distinguish between the quantitative results and explanations. These two major types of research output in physics, or broader in any advanced natural science, seem to be in a complementary relation in the spirit of the universal complementarity principle by Bohr. By explanation, we imply approximate replacement of a complicated system by a system which is simple, that is, possesses well-known properties and appealing to what we call physical intuition, or physical sense. If your computer is a black box, you load it with a code, it spits out some numbers. Even if they are in perfect agreement with experiment, you may not necessarily understand what's going on. But if the theory is sufficiently simple, you know what the ingredients are, you know how you built up you may call this model or approximation, then it really puts the physics to the fore. And the last bit, positron binding to polar molecules. This is all to do with understanding the details of positron annihilation in polyatomics. And I have to explain the intricacies of this in one slide, and in probably ideally less than a minute. Andrew Swan did this work when he was an MSI student. This is him graduating last summer. This is what experimentalists observe when they measure Z effective, essentially the annihilation rate, as a function of positron energy being in the range of 0.1, 0.2, 0.3 electron volts. And you can see a prominent feature in all of these graphs, measurements done for alkanes. You can see a peak. And you can also see, if you draw some vertical lines, that the peak gets progressively shifted towards lower energy with the size of the molecule. And this peak is shifted away from the frequency or the energy of the CH stretch vibrational mode, which lies at 0.37 electron volts. So what we're dealing with here is a resonance, or a bunch of resonances under the same envelope, and the progressive shift of these resonances to the left signifies the increase in positron binding when it gets itself trapped by exciting the molecule vibration. So the shift of the peak measures positron binding energy. Oops, there was a reference at the bottom. It really tells you all the details if you want to know them. Experimentalists by now, using this technique, they have measured positron binding energy for over 70 molecules. And when they plot these against the dipole polarizability, they observe some very strong trends that look like linear. So the experimentalists came up with the magic formula that cooks up the positron binding energy from some numerical constants, from the polarizability here, from the molecular dipole moment, which also enhances and taking away 5.6. When they further experimented with some polar molecules, and there are a few families, you can still see the linear trends with respect to the dipole polarizability, but you can see that the slope changes. So this formula, you can clearly see it breaks down. This is not 12.4. This is somewhat bigger for nitriles, it's somewhat smaller for alkanes. You can also plot the same delta as a function of the molecular permanent dipole moment, which makes it a bit messier and maybe disjointed. So what we're trying to understand here, these are all the quantum chemistry calculations available up to now. And what you can see in the second column, these are the dipole moments of the molecules for which calculations, quantum chemistry calculations have been done. Invariably, all the molecules are strongly polar. Of these, only 6 molecules have been measured. 64 molecules that do not have strong dipoles or are non-polar are sitting there, experimental data, awaiting explanation. What's going on? Why only polar? What's so good about polar molecules? Polar molecules will bind with positrons as long as the dipole moment is greater than the critical one. So binding is guaranteed. You pretty much don't even have to run the computer. You know that these molecules will bind, and then the question is merely the question of accuracy. So if we look at one example, the acetylnitrile, I'll magnify this for you. Quantum chemistry calculation from this paper gives the Hartree-Fock binding of 15 millielectronvolts, going up to 135 millielectronvolts with configuration interaction, and comparing reasonably well with the experimental 180. That's one of the very few examples where theory and experiment are in some tentative agreement. So what we wanted to do, having seen this picture from the same paper quoted on the previous slide, you can see how the positron sits outside the molecule. It doesn't really care about what the molecule is made of. There is a picture that we produced using Mathematica. This is the same positron wave function. It still doesn't care much about the molecule. It's a model potential. Forget the molecule. Use the dipole potential and cut it off at some small repulsive core radius, and this is what we explored. So when we did this, this is an approximate formula for the binding energy. You can plug in your dipole moments, A, B, C unknown coefficients. This is the graph of the binding energy. There is some preliminary account of the work, and the only free parameter to fiddle with is the radius of the repulsive core. Where is the molecule not letting the positrons in? And you can see how horribly bad these numbers are. This is supposed to be a physical quantity of the size of the atom, or of the size of half the bond length. They're all terribly small. So repulsive core radii are physically small. Once we saw there was a moment of despair, but then we realized there are other mechanisms of attraction. There is polarization-driven attraction. And when you include this even perturbatively, it makes values of R0 quite a bit greater. They are now of the order of 1, almost for ketones and aldehydes, definitely quite physical for nitriles. This is still bad. I'll be finished in a minute. What this formula immediately allows you to explore, the correction is linear in the dipole polarizability. So we can compare theory and experiment. Our model is black, experiment is blue. This is the kind of quasi-linear dependence on the polarizability of these species going across the families, and the slopes together are pretty reasonable. But if you really take a close look, this model describes its linear dependence. It can even make predictions. If you know the polarizability of your molecule, this is what you think the binding energy should be, but it is clear the correction due to the polarization potential is large, and you cannot really treat it perturbatively. And this is what Andrew is working on at the moment. So, unsolved, I had some conclusions along the way, but a very subjective list of unsolved problems involving positrons will be calculation of positronium formation in positron collisions with many electron targets, experimental discovery of positron atom-bound states. There are predictions of more than 10 of them, none have been seen. Observation of positron Feshbach resonances in atoms, there has been a prediction, they haven't been seen. Calculation of collisions involving positronium in Rydberg states, that's quite interesting because there are ongoing experiments and rapidly developing experiments on holding positronium for longer times because they would be excited in Rydberg states at UCL in London. Calculation of positron binding to non-polar molecules, this is a completely empty field. And then overall better understanding of positron annihilation in polyatomic molecules, how positrons couple to vibrations, especially in non-infrared active, non-dipole modes, how the vibration energy from positron supplied by the positron is redistributed following positron capture, etc. So there's still work to be done.